This image has long since become a global visual cliché. A countdown, plumes of white smoke, a blinding flash, and a multi-ton rocket slowly lifts off the ground, disappearing into the black sky. The launch is perceived as the push of a single button, a triumph of aerodynamics and pure intellect, where the launch pad is merely a temporary stand, a passive concrete pedestal for a technological marvel. But the television image hides the physical reality. If you remove the broadcast filters and look at the infrared spectra, the pressure sensors, and the micro cracks in the supports, the illusion of lightness vanishes. A launch is not a flight.
It is a controlled explosion of destructive force, from which not only the crew but also the planet beneath it must be saved.
Hidden crises occur seconds before launch. Liquid oxygen boils in the pipes, threatening to rupture the lines. An acoustic shockwave rebounds off the ground with enough force to pulverize metal. Concrete slabs crack from the instantaneous thermal shock. Hundreds of thousands of gallons of water evaporate in a fraction of a second, creating an impenetrable wall of steam. This is not just a construction site. It is a $50 billion infrastructure cluster functioning as a single, mechanically strained organism. A gigantic body of steel, concrete, and cryogenic veins, whose sole purpose is to absorb a massive dose of kinetic and thermal energy so that the rocket can survive.
By the end of this story, it will become clear why real space begins deep underground.
It will become obvious that the most complex engineering challenge is not to make the spacecraft fly, but to prevent the ground beneath it from turning into a crater. But to understand this, we must return to square one, to a time when there were neither launch pads nor water-based sound suppression systems, to empty, salt-soaked lands where gravity still dictated the absolute rules. The site for the first space ambitions was not chosen based on criteria of engineering convenience. Engineers dreamed of flat, dry plateaus, but harsh reality dictated entirely different conditions. Geography demanded incredibly tough pragmatism from the ambitious program leaders. The launch site vitally needed to be as close to the equator as possible to achieve significant savings in precious rocket fuel. The planet's natural rotation at these latitudes gave the heavy rockets an additional powerful boost at launch. An endless ocean was also required so that falling spent rocket stages would not kill civilians. This is precisely how the massive space infrastructure came to Florida's wild Atlantic coast. The chosen site turned out to be a real nightmare for absolutely any builder. It was completely undeveloped territory of deep, malaria-ridden swamps and very sticky quicksand. A thick, salty fog regularly blanketed the coast with a dense and incredibly damp veil. The local air was an incredibly aggressive, corrosive cocktail. The constant ocean breeze was thick with tiny crystals of caustic sea salt. With 100% tropical humidity, it began to mercilessly corrode even the strongest steel.
The process of rapid destruction began the very moment new parts were unloaded from the freight cars.
Ambitious engineers desperately tried to create the world's most precision-engineered technical system. And they had to do so under harsh conditions, where literally everything around them was rotting away. The great space infrastructure was, quite literally, taking shape in the impenetrable local mud. The very first launch pads were hastily poured by workers directly onto unstable, loose, sandy soil. Builders had to contend daily with constant landslides and soil collapses under the weight of heavy tracked vehicles. By modern engineering standards, these were very primitive concrete structures. They were designed exclusively for small vehicles the size of a standard short-range ballistic missile. The severe technological limitations of that era simply did not allow the builders to think decades ahead. No one back then was making grand plans to create a permanent infrastructure for future generations. All critical decisions were made in an incredibly frantic rush at the height of the Cold War. The main goal was simply to outpace the political adversary at any cost. A huge problem was protecting vital underground communication cables from the constant dampness of the marshes. To ensure reliable insulation, they were encased in a very thick layer of molten toxic lead. These heavy cables were then buried deep in freshly dug trenches, which were instantly filled with murky groundwater. A typical launch site in those early years looked more like a hastily erected temporary military camp. Piles of construction materials lay scattered everywhere, and flimsy temporary barracks for engineers stood nearby.
The tall metal rocket support structures rusted much faster than the painters could keep up with applying fresh paint.
The local wilderness constantly challenged human endurance and technical ingenuity. Ordinary technicians often worked literally knee-deep in murky, warm swamp water. They had to use long sticks to chase real alligators away from critical fuel lines and pumps. The flora and fauna actively resisted the arrival of high technology. Project managers at the time sincerely believed that this rough and primitive strength would be quite sufficient for launches. A concrete slab poured to a thickness of a full meter was considered an absolutely indestructible monolith. Engineers naively believed that such a foundation could easily withstand any rocket flame. But the very first successful orbital launches quickly revealed the complete illusory nature of these elegant calculations. The fiery plume of a powerful rocket engine behaved completely unpredictably. It did not merely heat the launch pad's protective surface to its limit. The incredible kinetic energy of the flame physically ground the solid stone into fine, volatile dust. The situation changed dramatically with the rapid transition to complex manned programs and very heavy launch vehicles. The total launch mass of all space objects on the coast increased exponentially. The old concrete shell of the spaceport began to crack menacingly at the seams under the new loads. The modest infrastructure of the previous decade simply could not withstand the colossal weight of the government's new political ambitions. The famous Apollo lunar program demanded the urgent creation of an entirely new, colossal infrastructure. All structures now had to be fully commensurate with the colossal Saturn V rocket. It was a fantastic machine, as tall as a full-scale 36-story residential building. To service such an engineering marvel, a special vertical assembly building had to be erected immediately. The interior volume of this incredible, gigantic structure boggled the imagination of even the world's most daring architects. Its scale was so vast that its own weather system could easily form inside.
Due to temperature differences beneath the soaring ceiling of the enormous hall, actual wet rain clouds would sometimes gather.
But the most significant and terrifying hidden problem lay deep beneath the building's massive foundation. Florida's soft and perpetually damp, swampy soil was physically incapable of supporting such a weight. We're talking about a colossal, constant load of many hundreds of thousands of tons of steel and concrete. There was a very real threat that the world's largest hangar would simply sink slowly into the mud. To prevent the massive building from sinking into the ground, the builders had to take radical measures. They brought in the heaviest equipment and began methodically driving thousands of steel piles into the soft local clay. These incredibly long pipes extended to an insane depth of over 50 meters. They plunged into the darkness until they finally struck solid limestone. The infrastructure began to put down real steel roots, but simply assembling the giant rocket in the hangar was only half the battle. This incredibly heavy and fragile structure still had to be transported with extreme care to the distant launch pad. To solve this problem, engineers created a unique tracked transporter weighing nearly 3,000 tons. Of course, such a cumbersome steel leviathan could not possibly travel on ordinary city asphalt. Under its incredible weight, absolutely any standard road would instantly crumble to pieces. The solid pavement would simply turn into a liquid, impassable mess in just one trip to the launch site. The ingenious engineers had to build a completely special track from scratch. For many long months, meter by meter, workers carefully laid out a complex, multi-layered structure for the future road. Its foundation consisted of thousands of tons of selected granite rubble, sand, and special round river stones. With every slow movement of the tracked transporter, this stone emits a deafening, eerily rhythmic crunch. It is the blood-curdling sound of gravity trying to crush matter. The sturdy river stones are mercilessly ground into fine dust under the monstrous pressure of the wide steel tracks.
Because of this, the unique road always requires regular and very expensive replenishment with fresh material.
The ground along the entire route has begun to deform under such a colossal load, unprecedented in history. A massive transporter with a rocket mounted on it sinks deep into the unyielding ground. The movement of the heavy platform is accompanied by powerful vibrations, creating local micro-earthquakes around the track. This was the first sign that the system was pushing beyond the natural physical limits of matter. But the real crisis of scale wasn't about weight, it was about temperature. With the advent of innovative rocket engines, the launch pad underwent a radical transformation. Engineers needed an incredibly powerful fuel to propel massive masses into orbit. The choice fell on liquid hydrogen and oxygen. Because of this, the launch complex quickly turned into a gigantic and very dangerous cryogenic pump. Capricious liquid hydrogen requires an unimaginable storage temperature of -253 degrees Celsius. In the conditions of a typical Florida summer with constant heat of 35 degrees Celsius, a colossal problem arises. The temperature difference between the fuel and the surrounding environment is nearly 300 degrees. This causes an incredible thermal shock to any material. Such a sharp temperature drop can shatter ordinary thick steel into small pieces in a matter of seconds. The metal becomes as brittle as glass and loses all its usual strength.
Engineers had to completely rethink their approach to fuel transportation at the launch site.
The entire launch complex system was hastily entangled with kilometers of complex piping. These were not ordinary pipes, but special double-walled structures with a vacuum inside. They operate on the principle of a giant thermos to prevent the liquid ice from boiling. The entire space infrastructure was equipped with a complex artificial circulatory system. Through these long arteries, powerful pumps continuously circulate a coldness completely unnatural to our planet. Technologically, this was a true marvel of engineering at the time. In the bright light of the nighttime xenon floodlights, these dark highways look truly terrifying. They quickly become covered with a thick layer of solid white ice, formed directly from the humid tropical air. A ghostly fog constantly shrouds the launch tower during the long refueling process. Ice rapidly forms in massive layers on all accessible surfaces of the pipes. This critically increases the weight of the complex's supporting structures by many hundreds of kilograms. The designers had to urgently reinforce the frame so it wouldn't collapse under the weight of the ice. Under such extreme conditions, conventional building materials began to behave completely unpredictably. Upon contact with sub-zero temperatures, the long steel pipes deform catastrophically. They physically contract by several centimeters due to the sudden and severe cooling. During this contraction, the massive metal constantly emits very sharp and frightening clicking sounds. Engineers watched in horror as the metal colossus constantly changed its physical dimensions. Under such intense stress, the heavily bolted valves would simply be torn from the pipes with a loud crash. To save the expensive system from inevitable self-destruction, they had to urgently find a non-standard solution. engineers devised and widely implemented so-called expansion joints. These are special, flexible, corrugated sections, very similar to the bellows of an accordion. They allow the rigid metal pipes to expand and contract freely as temperatures change. Thanks to this ingenious innovation, the entire cumbersome infrastructure of the spaceport literally began to move. The metal structure smoothly stretches and contracts, adapting to extreme conditions. The entire system now compresses heavily during the refueling of icy cryogenic fuel. And just as easily, it expands with great relief when the fuel is drained after a launch is cancelled. However, the tension at the launch site never subsides until the very moment of launch. Under such enormous loads, any accidental microscopic leak in the system is always fatal. Ordinary oxygen in ultra-high concentrations radically alters the properties of familiar materials. It instantly makes absolutely everything around it highly flammable, including asphalt and the fabric of protective clothing. Even greater danger is posed by the capricious hydrogen itself.
This treacherous gas is completely colorless, odorless, and extremely volatile.
When ignited, it burns with a transparent flame that is completely invisible in daylight. The electronic fire alarms of those years could not always detect this threat in time. To identify such a deadly leak, technicians in the past resorted to desperate measures. They took the most ordinary brooms and used them as primitive flame detectors. Engineers held these brooms far in front of them with outstretched arms. People moved slowly forward during the mandatory inspection of the launch pad. If a dry straw broom suddenly flared up brightly, it was a clear alarm signal. It meant that an invisible wall of fire was raging directly ahead. As a result of all these dangerous processes, the launch pad finally ceased to be a static object. It turned into a gigantic, highly stressed membrane made of durable concrete and steel. This complex mechanism is forced to balance on the brink of disaster every second. It is tightly squeezed between the absolute cold inside the thin tubes and the exhausting subtropical heat outside. Constant critical overload has become the absolute norm for the entire infrastructure. It has become the permanent state of the entire vast space complex. Only the incredible precision of the engineering calculations keeps this system from destruction. The launch pad stands frozen in anticipation of liftoff, like a coiled metal spring. The true destructive power of the launch lay not in the flames. The main invisible enemy of the new space age turned out to be the most ordinary sound. The engines of modern super-heavy rockets generate monstrous acoustic waves. The density of this sound energy surpasses almost all natural phenomena on Earth. At launch, the sound becomes so dense that it turns into a solid physical object. The air transforms into an invisible sledgehammer that delivers crushing blows to the complex. The noise level at the epicenter of the launch reaches a staggering 200 decibels. By comparison, the sound of a passenger plane taking off is many times weaker and safer. This is a critical level at which sound pressure can easily shatter concrete slabs. Moreover, such powerful vibrations turn human organs into a pulp. Being near the launch site without reliable shelter became deadly dangerous. The sound began to pose a real threat, even to the spacecraft itself, as it flew into space. During the very first test launches of super-heavy launch vehicles, scientists sounded the alarm. Engineers encountered a completely unforeseen and very frightening physical phenomenon. A powerful sound wave from the roaring nozzles rushed downward at tremendous speed. It crashed violently against the solid concrete bottom of the deep exhaust duct. After that, the wave bounced harshly back upward, losing none of its penetrating power. This acoustic energy struck the rocket's metal body with terrifying force. It turned out that the incredibly expensive machine had begun to mercilessly destroy itself. It was rapidly being destroyed by its own echo reflected from the ground. The reflected acoustic energy proved capable of instantly destroying even the most delicate electronics. Onboard computers and precision navigation systems simply failed due to the vibrations. The sound could easily tear the huge full fuel tanks to shreds. And this could happen even before the spacecraft left the launch tower. The old gas venting trench could no longer perform its intended functions. This gigantic deep trench, made of expensive refractory bricks, was hopelessly outdated. It proved completely powerless against such new and all-consuming destructive vibrations. It became absolutely clear to the engineers that the spaceport urgently required large-scale and radical infrastructure surgery. Without a fundamental redesign of the entire site, future launches would be impossible. The system had reached the brink of collapse, where continuing flights meant certain disaster. The attempt to save the rocket from acoustic death gave rise to one of the most complex engineering solutions in history: a water-based sound suppression system. It turned out that only enormous masses of fresh water were capable of effectively absorbing and dissipating the incredible kinetic energy of the acoustic shock. The roar of the giant engines is so powerful that the sound waves can literally tear the spacecraft's hull to pieces. The intense vibration from launch can easily unscrew steel bolts and destroy the most delicate electronics. Therefore, engineers had to create a veritable controlled artificial flood at the launch site. Cyclopean water towers sprang up very quickly around the launch pad. These giant steel tanks were designed specifically for the safe storage of colossal volumes of liquid. Their main and only task is to dump millions of liters of water onto the site. And this must be done in a matter of seconds before the historic moment when the engines ignite. This is far from just a light, refreshing shower to cool the scorching launch concrete. It is a real, controlled tsunami, rushing out of steel pipes 2 meters in diameter. The rushing water fills a special trench and creates a very powerful, life-saving acoustic cushion. It physically breaks the deadly invisible sound waves into countless tiny, completely harmless bubbles. The air vibrations rapidly lose their intensity upon abrupt contact with the denser liquid medium. The noise of the running engines gets bogged down in this solid wall of water and loses its destructive power. The sound literally drowns and dissolves without a trace in this raging man-made torrent. But this ingenious solution inevitably created a new extreme load on the entire structure of the launch pad. When the roaring flame of a rocket engine strikes the wall of water with force, true chaos ensues. The exhaust temperature of modern rockets reaches an incredible 3,000 degrees. Under such extreme, scorching heat, enormous masses of liquid evaporate almost instantly. The volume of water increases catastrophically by a factor of 1,700 in a fraction of a second. This incredibly rapid physical expansion results in a colossal steam explosion of immense power. The immense energy seeks a quick outlet and rushes rapidly through special discharge channels. The white plumes, which TV viewers often mistake for thick smoke from the engines, are actually something else entirely. It is simply high-density superheated steam, consisting entirely of minute droplets of rapidly boiling water. With a deafening roar, it bursts out of the deep exhaust channels of the launch complex at the speed of a powerful hurricane. The dense, scorching stream of steam sweeps away absolutely everything in its path. A huge white cloud rises hundreds of meters above the ground. From a distance, this massive spectacle looks incredibly mesmerizing and extremely frightening at the same time. The price of this elegant rescue is colossal physical wear and tear on all the launch pad equipment. The turbulent stream of steam mercilessly washes away the durable refractory sealants from the joints of the thick concrete slabs. The powerful shock wave from the water, falling from a great height, easily deforms the massive metal guides. The entire multi-ton structure is subjected to terrifying vibrational loads at the very limit of its physical capabilities. Acidic residues from the combustion of rocket fuel inevitably mix with the flows of processed water. This liquid mixture turns into an incredibly corrosive suspension that aggressively corrodes absolutely everything in its path. Every successful launch has become an act of partial, inevitable self-destruction for the massive launch pad. It has proven completely impossible for engineers to send a heavy rocket into space while keeping the site in a perfectly pristine condition. The costly ground infrastructure must be sacrificed to save the spacecraft itself as it soars into the sky. After every long-awaited triumphant launch, the infrastructure is in desperate need of urgent and extremely large-scale restoration. As soon as the hot steam dissipates, special teams of experienced inspectors immediately enter the damaged site. They carefully assess the massive damage inflicted on the equipment and draw up a detailed plan for restoration work. The long process of replacing the heavy refractory bricks, which have been torn out by the roots, and pouring fresh concrete begins. Repair crews sometimes work around the clock on the complex welding of steel pipes torn apart by terrifying pressure. They also have to completely relay and restore the burned electrical cabling. The launch site truly survives after every incredibly powerful space launch. But at the same time, the entire complex system irrevocably loses its precious initial lifespan with each new launch cycle. Fatigue in the durable metal gradually but inexorably accumulates in the most critical load-bearing components. At the same time, an ambitious space shuttle program was underway, introducing a new toxic variable into the established system. This involved massive side-mounted solid fuel boosters and a highly specific toxic hypergolic fuel. These new chemical components radically changed the strict daily safety protocols at the spaceport. All ground logistics were forced to urgently adapt to working with highly dangerous materials. Because of these new technical solutions, the infrastructure began rapidly accumulating a dangerous toxic legacy. The day-to-day maintenance of giant rockets became exponentially more dangerous to human health and life. The products of the aggressive combustion of the space shuttle's winged booster rockets contained a truly colossal amount of harmful substances. The thick exhaust produced the most pure gaseous hydrochloric acid. With every new historic shuttle launch, a veritable acid rain fell over the site. This dense toxic cloud settled very slowly and completely inevitably on all the exposed structures of the launch complex. The wind easily carried this harmful mist many kilometers around the launch zone. The surrounding local environment also suffered greatly from such dangerous chemical fallout. This regular corrosive acid rain caused completely irreparable damage to the highly complex and very sensitive equipment. It instantly corroded the freshly applied paint and aggressively destroyed the expensive protective galvanizing on critical metal parts. The dangerous concentrated acid mercilessly penetrated the tiniest microcracks in the old, sturdy concrete foundation. There, it immediately began its hidden, invisible, destructive work anew each day. As a result, the massive steel skeleton of the launch complex began to rust rapidly from the inside out. Stopping this destructive process required colossal physical effort and enormous financial resources from the people involved. The shuttle's own orbital maneuvering systems used liquid hydrazine as their primary propellant. This corrosive chemical was so incredibly toxic that it always required absolutely unprecedented safety measures. All highly trained technicians could work with hydrazine only in fully sealed, heavy-duty protective suits. This complex and cumbersome professional gear bore a striking resemblance to actual military chemical protection equipment. Inside such a suit, internal pressure was constantly maintained and clean air was supplied from tanks. A routine refueling operation had forever turned into an extremely complex and incredibly dangerous military operation. The slightest technical error during dangerous work with treacherous hydrazine could instantly lead to a massive catastrophe. The complex pumping equipment had to remain absolutely airtight at all stages of transferring this toxic liquid. A single drop of hydrazine on gray concrete immediately triggered a full-scale emergency alert across the entire launch base. It required an urgent, immediate, and extremely lengthy procedure, lasting many hours, to completely chemically decontaminate the contaminated area. Specially trained personnel had to thoroughly wash away and completely neutralize the spilled poison using special, expensive chemicals. Only after this was the cleaned concrete area officially recognized as completely safe for further work. The spaceport's infrastructure had definitively and irrevocably lost its former appealing technical simplicity. The vast work area very quickly became overgrown with dozens of redundant systems of reliable gas analyzers. Emergency wash stations appeared practically everywhere for the rapid rinsing of toxic acid from affected personnel. Engineers also specially constructed highly complex airlock chambers to ensure the safe passage of personnel. This entire incredible system of tangled pipelines began to visually resemble the gloomy sets of a science fiction film. The old, tried-and-true launch complex gradually turned into a gigantic, high-security, closed laboratory. At some crucial turning point, the daily complexity of ground support significantly exceeded the complexity of the rocket itself. Keeping this entire massive, sprawling system operational required a huge number of highly qualified specialists. This entire cumbersome network of pipelines became extremely vulnerable precisely because of the vast number of interconnected mechanisms. The sudden failure of even a single small, sensitive sensor could paralyze the entire complex for a long time. The infrastructure ceased to be merely a reliable, silent support for a powerful space rocket. The system became fragile due to the number of elements, each of which could cause a launch to be cancelled. Today, the space industry is indeed undergoing a powerful tectonic shift. The era of new super-heavy rockets has permanently closed the old chapter on the use of conventional concrete. Modern systems, such as those developed by Elon Musk's company, have required a completely different approach to the construction of ground facilities. The scale of rocket thrust has grown to such extremes that previous engineering compromises simply stopped working. Now, spaceport builders have to invent methods that once seemed like pure science fiction. Old safety standards are no longer capable of containing the furious power of the new engines. During the first orbital test of the new Super Heavy system, a veritable catastrophe struck the entire ground infrastructure. The concrete foundation of the launch pad did not merely crack under the weight of the steel giant, it literally exploded under the influence of colossal temperatures and incredible pressure. The combined force of 33 engines turned the high-strength reinforced concrete into dangerous shrapnel. Huge chunks of the foundation flew for kilometers in all directions, destroying expensive communications and refueling equipment. The ground beneath the launch pad simply could not withstand such a powerful and concentrated blast of flame. After this incident, engineers needed a fundamentally new approach to structural integrity for the entire site. Massive and incredibly strong steel replaced the conventional concrete. The modern infrastructure now consists of highly complex, multi-layered steel plates with special heat treatment. A unique active water cooling system is built into these massive structures. Externally, this entire massive metal structure resembles a giant upside-down showerhead. This technological solution became the only way to protect the launch complex from instant vaporization upon contact with fire. The principle behind this system is striking for its technical elegance and brute force at the same time. Cooling water is now fed onto the launch pad, not just from above to dampen the sound. It surges from below under immense pressure, directly into the searing flame of the rocket's firing engines. Engineers are attempting to counter the destructive energy of the flame with a powerful counter-water jet of a massive volume of liquid. This creates a sort of dynamic water shield that absorbs the main thermal shock. Without such active protection, the steel plates would burn through in a matter of fractions of a second. We are now witnessing the true pinnacle of physical and technical overload on structural components. The pressure in the water lines is so great that the thick steel pipes themselves become potential bombs. The entire ground infrastructure has turned into a complex mechanism for actively countering destruction. It is forced to operate under the same extreme conditions as the rocket itself as it launches into space. The slightest malfunction in the water supply system will lead to the instantaneous destruction of the entire launch pad. Designers must take every detail into account when designing these highly complex safety systems. These days, a launch pad is no longer just a passive foundation for launching a spacecraft. It actively, and even quite aggressively, resists the force of the spacecraft as it takes off. This has turned into a veritable battle between two titanic engineering systems. One side attempts to break through the Earth's surface with its incredible thrust of millions of kilograms. At the very same moment, the other system pushes upward a wall of cold water and hardened steel. The main goal of this struggle is to maintain the structural integrity of the facility and save the expensive spaceport from complete destruction. The television broadcast ends. The rocket pierces the stratosphere. The cameras switch to onboard views of the blackness of space. The viewer gets their inspiring finale. But on the ground remains the true artifact of this process. Molten steel, charred carbon on blackened supports, clouds of settling toxic vapor. Water pumps gradually slow down. The metal in the cryogenic lines groans as it returns to its natural volume in the warm air. This cluster, worth tens of billions of dollars, is not merely a foundation for rockets. It is the ultimate physical limit of humanity's capabilities. A monument to the fact that gravity will not yield a single kilogram of mass without the most fierce resistance. The symbol of the technological future is not hidden in the gleaming cylinders of spaceships. It is buried deep within the scarred concrete, in the pipes torn apart by acoustics, and in the constant cycle of destruction and restoration. The price of space is always paid on Earth, and this Earth is forced to transform, grow more complex, and die with every new launch, so that flight remains possible.